today I'm very happy to introduce Onur Mutlu, who is a professor of computer science at ETH. And he is also a faculty member at the CMU, where he previously held the Stryker early career professorship. And his current broader research interests are in computer architecture, system, and bioinformatics. A variety of techniques that he, along with his group and collaborators, has invented over the years, have influenced the industry and have employed in the commercial microprocessors and memory and storage systems. So he obtained his PhD and the master from the ECE department of UT Austin, and the BS from the computer engineering and psychology from the University of Michigan. He started the computer architecture. He started the computer architecture group at Microsoft Research, and held the various product and research positions at, for example, Intel Corporation, AMD, VMware, and Google. He has received many awards that included the inaugural IEEE Computer Society Young Architecture Award, and also the inaugural Intel Early Career Faculty Award, the NSF Career Award. So he is a fellow of the IEEE and ACM for the fundamental and outstanding contribution to the computer architecture, especially memory system. He is also elected as a member of the Academy of Europe. So today he will be talking about the modern computer system that enables the in-memory computations.
Thank you very much, Yohai, for the introduction, and thank you for being here. It's early in the semester, as I understand. This is my first time at USC, actually. Yeah, I've never been to the campus, so it's a pleasure to be here. And I'll enjoy the nice weather in LA in the meantime. Okay, this talk is something that could go on for days, but I will not. Feel free to stop me with questions. I think we have 2 hours or so, or a bit less. But I'll give you an overview of some of the things that we're doing in memory computation. A lot of this is going to be motivational, because this is not a new idea. It's actually a very old idea. It goes back to analog computation in the 1940s, 50s, and it's reoccurred many times. So hopefully I'll give you a different context to why it's important to do it today, maybe in a different way also than people have been thinking about in the past. But before I start, these are some of the things that me and my group work on. This is a slide that I used to present at CMU for incoming students. It covers a bunch of topics, and we're going to touch a bunch of these topics over here, especially memory and storage. We're going to talk about DRAM quite a bit, but a lot of the ideas that I'm going to discuss will be applicable to emerging technologies. And I'll give you some examples when we get to it. We're at a very interesting intersection today in terms of hardware security, energy efficiency, fault tolerance, and performance. These are pulling us in many different ways, and I think I'm going to motivate this talk partly in memory computation, talking about some of these issues. Actually, we're going to touch upon a lot of these, and we're going to talk about system architecture interaction, new execution models, new interfaces that are needed to enable those new execution models processing in memory, and by definition we're going to talk about parallel and heterogeneous systems, and we do a lot of work on GPUs. I'll touch upon a little bit of that, and pretty much everything that we discuss will be on data analytics, if you will. I do a lot of work on genome sequence analysis and assembly algorithms and architectures also. Actually, I'm going to use that as a motivating detour to start this talk from the application perspective. And this is something that I'm not going to talk about that's very interesting also. Okay, basically these are some of the four key directions that we're following in my group. It's not comprehensive by any means, but we're going to touch upon pretty much all of this in this talk. Fundamentally secure, reliable, safe architectures, energy efficient architectures. I think this means data-centric or memory-centric, and low latency architectures, and architectures for genomics, medicine, and health. I'm going to use this last one as I mentioned, as a motivating detour to motivate processing in memory a little bit. This was the dream we had, actually, when I started as a fresh PhD after school, after graduating from UT Austin, while I was hiking with one of my friends, Mount Rainier. He was in the field of genomics, bioinformatics, and we wanted to actually, we were brainstorming, we wanted to have an embedded device that could perform comprehensive genome analysis in real time. Of course, not hard real time necessarily, but something within a minute, let's say. And at the time, even the simplest part of the genome analysis was taking like weeks on a laptop, and if you parallelize it, it would still take a long time, but you would consume a lot of energy, of course. So there are many things that could go into genome analysis, like which of these DNAs does this DNA segment match with, what is the likely genetic disposition of this patient to this drug, and you can imagine many, many other questions that could build on this, and people are actually trying to do more with this. And we wanted to do this in an embedded device. It's not easy, I think. And I'm going to get back to the stream later on. We're still following the stream. At that time, even the technology of the genome sequencing didn't exist in a small scale. All of these genome sequencers were large. And I'm going to show you examples of this very quickly. I'm not going to go into a lot of detail in this part of the talk other than motivating a potential application that we don't have today that could potentially be enabled by designing better systems. So I'm not going to go through this in detail, but everybody has these genomes. And we have base pairs, ACTGs. And this is a real one. This is very interesting, actually. There are a lot of stories in genomics. This is Henrietta Lacks' genome, which was taken from her without her consent. So there are a lot of privacy issues. But this actually enabled a lot of progress in genomics. By analyzing her genome, people have figured out a lot of interesting things. So basically, in genome sequencing, the goal is to find the complete sequence of these bases or base pairs in someone's DNA, ECGTs. The challenge is there's no single machine that exists yet, at least, that takes the long DNA as input and that gives you the complete sequence as output. If you look at a long DNA, it consists of about 3.2 billion base pairs, and you cannot get 3.2 billion base pairs with any technology today. All sequencing machines are essentially choppers. They chop the DNA into small pieces with different granularities, we'll see that, and identify those relatively small pieces with some level of accuracy, different level of errors, but they do not tell you how those pieces fit together. So essentially you have a computational puzzle. Your puzzle is to figure out where those pieces match in the genome and reconstruct the complete 3.2 billion base pairs. And if you look at the length of these small fragments that they chop the DNA into, it varies based on the machine. Sometimes it's 100 or 200 base pairs. Sometimes it's 100,000 or a million base pairs. So it's very much dependent on the technology. But it's a difficult computational puzzle. I liken this to untangling yarn balls. If you have a cat that's playing with these yarn balls, you can chop these. You cannot get a single yarn ball in a full sequence, but you can get pieces of it. And these are the choppers that we have today. This is actually one of the most powerful ones, maybe not the most powerful at this time. You pay $3 million for it. It gives you fragments of size 300 or so. Its error rates are relatively low, so you can relatively be sure that those 300s are actually what you're really getting. And this didn't exist when we were dreaming, actually. So we believed in the technology, and this now exists, so this fits in your hand. It's about $1,000, $2,000. You can actually do some of these studies yourself. It gives you long fragments, like 100,000 or a million. But its error rates are relatively high right now. It's 15% or so. So of course, having long fragments is good because you can match things much more easily that way. But if your error rates are higher, then you're back to the computational puzzle that makes it difficult to really reconstruct the complete sequence. So basically, you have a trade-off at hand. And all of genome analysis, everything that comes after it depends on this. Essentially, we know how to build these sequencers today, at least to some granularity. It's not perfect. It's chopping the genome, and it's giving us a lot of short reads or some long reads with some error rate. And then we need to map these to understand how these things fit together. And then we can do analysis on top of that. Basically ask the question, okay, does this part of the genome indicate a disease for this individual? Or if I actually apply this drug at this critical moment, will it actually affect this patient in a good way or a bad way? That could be one example. And this could also lead to scientific discovery. But we're really bottlenecked at this point right now. So this is one example of sequence alignment. This is called metagenomics. Basically, you can examine different species genomes and try to identify how they match together. But essentially, we know how to do this relatively well today, but we don't know how to do this very well. We're basically bottlenecked in the mapping. And don't get too much stuck in the numbers over here. It depends on the technology assumptions. Basically, we're really bottlenecked at this point over here. So when we actually first started this research, our goal was to construct a read mapper that's fast and comprehensive. What does comprehensive mean? Comprehensive means that whenever you actually get these fragments, they may match many, many potential positions in the genome. And we didn't want to miss anything over there, because if you miss something, you may miss a potential variant that could actually be indicative of something. So we want to design that mapper. That's what we designed when we first started. This is actually relatively old work from 2009. This was the most comprehensive mapper at the time. It's guaranteed to find all mapping. It's very sensitive, but it's slow, like many, many other mappers. If you want to find a lot of the potential mappings, it becomes slow. And we analyzed the execution time of this, and it turned out most of the execution time is spent on read alignment. Basically, you try to match small parts of the genome with a reference genome, and essentially we're trying to do the alignment process, and that's edit distance computation. All of you probably know Hamming distance computation. That's relatively cheap. Edit distance computation is trying to find what is the distance between these two strings in terms of how many insertions, how many deletions, how many substitutions you need to do to get from this string to this reference string. And that's actually a dynamic programming problem, and that takes a lot of time. And our idea was actually, and at that time actually there were a lot of specialized architectures, for example FPGAs, that tried to accelerate this. We wanted to take a different path, and our idea was to try to get rid of this computation as much as possible. And the idea is very simple. Basically, it's to design an architecture that does this in two steps. The first step is filter. It's a filtering step that basically quickly checks whether this fragment matches this part of the genome or not. And you can do this in many ways. There are many ideas. I'm not going to go into the detail. So that if you actually do this nicely, you don't need to do the comparison, approximate string matching that you need to do at the end. So our goal was to minimize costly approximate string comparison. So we started to design these filters. Our first filter was actually a software-based filter. It's all available online. All of the source code is available online. You can download and try it for yourself. And we were actually exploiting the structure of the human genome to test, to build an index of the genome and actually test whether the fragment that you're getting from the chopper is matching these locations. So by doing very simple tests, you can actually get rid of a lot of the alignments. And this filter actually accelerates the read mapping process by about 20x by quickly testing whether you're going to match or not in some particular location. And later, I don't mean to go into a lot of detail over here. I'm just going to give you the process of exploration that we did. Later, we said that this is not enough. This is purely software-based, so we wanted to actually accelerate this alignment filtering step with some data structures that are much better fit for bitwise operations that could be done relatively fast using SIMD instructions. And this is the filter we designed in the end. I'm not going to go into the details of the ideas. It's actually a very cool idea. As opposed to doing this edit distance computation, you can convert the edit distance computation to multiple Hamming distance computations, which are much easier by shifting the strings that you're comparing to the left and right, so that you can find the insertions and deletions. But it's not perfect. As a result, this is a filter, and this filter can be very fast. And this actually speeds up the read mapping process by another 3x or so. And later, we went into actually FPGAs, and this is a work we published in 2017 that does this filtering in a much faster way by exploiting the FPGA architecture by changing the algorithm to actually do that. And this actually speeds up your mapper by about another 10x or so.
Can you give an idea of the size of the mappings that you're doing in terms of the sequences?
Sure, yeah. So basically, we are looking at short read mapping. This is 300 base pairs long, and you're trying to match, figure out where this 300 base pairs occurs in the reference genome. Yeah.
Right.
Yeah. So it's actually a lot of computation in the end.
In the software approach, how was the runtime on that, and what kind of machine?
Exactly. So that's a very good question. It depends on the machine. So we want, if you're doing on a laptop, and it depends on also on the variations that you want to find. Usually, a lot of the mappers that are used today actually are exact matchers. They try to find the exact matches, but we wanted to actually allow up to, let's say, 5% errors. So 15, there could be 15 base pair mismatch between the source fragment and the reference fragment. And if you actually do that, that increases the runtime of the mappers quite a bit. So with a laptop, state-of-the-art laptop, it takes about 2 weeks or so to do that. And we actually, all of the algorithms combined, I'll say that later, speeds that up by about 200x on average.
You did this on an FPGA, you said?
Exactly, yes.
And what was the runtime there?
So that actually reduced the runtime to less than a day. Okay, but basically we're, hopefully that gives you an idea. Basically, you're heavily bottlenecked by the data movement in all of these approaches, especially when you optimize the software. So a gatekeeper FPGA performance is very much limited by the DRAM bandwidth. That's true for this shifted timing distance approach on SIMD architectures. And the solution that we're following right now is actually processing in memory, and it could alleviate this bottleneck. However, of course, we need to design the mapping and filtering algorithms to fit processing in memory. And that's exactly what we did in a recent paper that was published last year in the Asia Pacific Bioinformatics Conference. I'm not going to go into detail, but this actually overcomes that memory bandwidth bottleneck and gives you another speed up between 3 to 10x or so. I'm not going to go into the detail, but I just want to motivate this particular application. This is just one of the applications that I believe is bottlenecked by memory and that could be enabled potentially. I'm not going to go into this detail. The slides will be available if you're interested. But yeah, the overall, at this point, we're around about a 200x speed up in mapping time, sometimes more, sometimes less, depending on the input data set. But we need more. So right now, we're actually looking into these devices that didn't exist when we were dreaming about 12 years ago. These devices are actually very promising, I think. Today, people are using these nanopore sequencing devices to actually sequence viruses, for example, in Africa. Unfortunately, the processing power, there's no processing power on the device, and the processing power on a laptop that they're plugging the device into is not enough. So what they're doing is they're shipping all of that data to data centers in the US or somewhere to process that data. And I believe they're exacerbating all the bottlenecks that we have in the world in terms of energy and sustainability by doing that. If you had processing in this device that could actually give you very quick results, why communicate all of that data everywhere, other than storing it maybe? Okay, so I'm very excited about this device actually. It's very interesting. All of these devices have actually very interesting characteristics in terms of how they figure out what's an A, what's a C, what's a G, what's a T also. But this is something that you can experiment with also. And we recently analyzed the tools to actually perform analysis, genome analysis using this device. And we've written this paper. If you're interested, you can take a look at it. But what I've been so far talking about is just part of the pipeline. Actually, this device has other bottlenecks as well. Finding out ACTGs, this is called base calling. That takes a long time. And there are actually a lot of machine learning-based algorithms over here that are really interesting. But basically, there are bottlenecks everywhere over here in the genome analysis. So I don't want to go into a lot more over here. There's a much longer talk that goes into a lot more detail that I'd be happy to give some other time. But let's go back to our dream that we had. Are we there yet, basically? I don't think so. Even though we have the technology, I think the computational bottleneck is so strong that we still have a long ways to go over here. We want to be extremely energy efficient if we want to do this in an embedded manner. Performance is a big problem. And we haven't even talked about the security or privacy issues over here, let alone. But we need to, I think, tackle these two first. And I think because of the huge memory bottleneck, we need to overcome the huge memory bottleneck to enable an application that looks like this. We have to process at the point when we actually get the data. We don't want to move the data farther than it's really needed. And that's one motivating application for my talk. I'm going to go back into some other applications. But I believe it's a forward-looking application that doesn't exist today. That's why I wanted to motivate the talk with this. So let's go into, yes, Michelle.
So you say what you're trying to do is to accelerate this procedure, but is it really useful? I mean, what kind of environment do you really need to do that very, very, very quickly?
Yeah. So that's a very good question. I don't know the full answer to that question. I see this as an enabler. If you have this device, it could enable potential applications. But one application that I could potentially see is if you're in a life-critical situation, for example, if you need to do this genome analysis to understand what kind of drug you need to use in a patient. Today, that analysis takes a long time. And also, it's not very affordable as well. on top of the long time. And I think affordable part is related to the computational problem as well. So my feeling is it could accelerate, you really need acceleration in those cases, in life-critical situations, for example. But there could be other use cases. If you accelerate the entire process, you actually reduce the time to discovery of certain things. Today, people actually don't even, a lot of the bioinformaticians actually don't even try to do the full analysis. Today, they try to, essentially they use mappers that are exact matchers. So we don't even know what we're missing at this point, in my opinion. But that's a study that I would like to do also once we have some of the mechanisms in place.
So the whole talk here is going to be about an architecture that compute the genome.
Not this talk. Now I'm going to pull back.
Oh, okay.
I'm going to talk about the general processing in memory. But this is one example application that I believe is very much bottlenecked by memory.
Sure.
And that could actually accelerate, that could benefit from processing in memory in a significant way. I have another talk that talks about all of the mechanisms that we developed to accelerate genome analysis, but that's not what I intend to talk about going forward. So, okay, I intend to talk about more general purpose right now, and we're going to go into special purpose when the time comes. So I'm going to talk about main memory. It's a critical component of all computing systems that we have today. Whatever system that you have, server, mobile, embedded, desktop, sensor, you need some sort of working storage. It's usually DRAM based today, main memory. And this system, main memory system, must scale in many dimensions in terms of capacity or size, technology, energy efficiency, costs, and algorithms we use to manage it. If you want to maintain the performance growth and the technology scaling benefits that we're used to, and if you want to enable new applications that do not exist today. And it doesn't matter what you attach to it today, GPUs, FPGAs, CPUs, or a heterogeneous combination of these different types of accelerators. We're bottlenecked by this interface. This is another picture, this pictorial view that I drew with XFIG. It's not very nice, but I'll make 2 points over here. If you look at a system that looks like this today, most of the system is really dedicated to storing and moving data. If you look at the parts that do computation, it's limited to these cores over here. Everything else is there to store data, move data, store data, move data, control the data, storage and movement, move data, store data, move data, store data. Basically, only the red parts over here are doing computation. Even in those red parts, a lot of those red parts are dedicated to moving and storing data. L1 caches, register files, interconnect inside the cores. We're designing these systems, we call them computing systems, but most of the system is really dedicating to not doing computing, storing and moving data. And this is, we will get back to this picture later on. And the second thing is, over here is that the system that stores and moves data is shared across the computation unit, so it becomes another bottleneck in terms of quality of service and predictability, which I'm not going to go into in this talk as much. Okay, so this is in one slide the state of the main memory system as I see it today. There are some new technology, architecture, and application trends that lead to some new requirements from the system that exacerbate old requirements. And we've always demanded a lot from the system. We're demanding a lot more going forward. I'm going to cover this in a little bit. I will hopefully show you that DRAM, the main technology that we use to design main memory, and memory controllers, as we know them, as we design them today, are already failing to satisfy all of these requirements. And on top of that, there are some emerging memory technologies that happen to be non-volatile that enable new opportunities, like merging of memory and storage. I'm not going to talk about this. I believe this is very, very exciting, but that's a part of the talk that part of research that I'm not going to touch upon today. But there are also other emerging technologies that could enable some other things that could circumvent some of the issues with DRAM. So given these trends, I believe we need to rethink the main memory system and the systems we're designing around it for a long time to fix the issues we're having with DRAM and to enable some of these emerging technologies, while of course satisfying all the requirements that we have from the system. So let's take a look at some of these trends. Again, this is in my opinion, these are the three major trends that are affecting main memory. We have an increasing drive for memory capacity, bandwidth, and quality of service. And that's not going to end. This is driven by the fact that computation is relatively easy today. We know how to put many, many cores on a chip. Moore's law has enabled that, and we've actually figured that out very well, I think. And actually, we're not putting more cores because of the memory bottleneck sometimes. Applications are becoming increasingly data intensive. That's not going to change. And if you want, and the application that I gave you, the genome analysis is actually becoming increasingly data intensive because people are actually sequencing many, many more genomes. They want to compare more of them. It's actually, we can actually sequence genomes much faster than we can actually analyze them today. Yes?
So in the case of the multi-core, so you're talking about a single chip with 7 cores on it, right?
Mm-hmm.
So in that case, isn't it the major limitation is really the number of things, the bandwidth in and out of the chip?
So I would agree with that, yes. And that's really the memory bottleneck, sure.
Okay.
Absolutely. I'll give you an example of that in a little bit. And whenever we design a system, we want to consolidate more and more. That's true for many computing systems today. And that's driving the capacity, bandwidth, and quality of service requirements up, all of these together. This is one example graph that's relatively old right now from HP Labs at the University of Michigan that were in a paper they published in 2009. They basically showed that core count is doubling much faster than DRAM DIMM capacity. As a result, you don't have enough capacity per core, which is not good news for software because software has relied on having more capacity per thread. Otherwise, it becomes difficult to write software. And you could argue with these numbers over here. Actually, it's a really good exercise sometimes to think about it. Is it really the same way? Depends on which architecture you're looking at. In GPUs, actually, the core counts are increasing really fast, but memory bandwidth is also increasing, but not as fast. In CPUs, sometimes this may not be true, but maybe because we have a memory bottleneck that we're not adding more cores. So these things are related as well. If you actually look at the trends for memory bandwidth per core, they're much worse. Memory bandwidth is not increasing even as fast as the memory capacity. And this is an example graph. Let's have some fun with this particular graph. So basically, we're going to analyze the trends in DDR, the most common technology of DRAM memory that is manufactured and used in the last 18 years. And we're going to look at the improvements in capacity, bandwidth, and latency. How much do you think capacity has improved over the last 18 years in the common DDR technology? Any guesses? 40 times, I heard. 1,000 times. And the real answer is somewhere in between. It's basically 128x. And this is where DRAM manufacturers are designing their chips for, right? They want to actually reduce cost per bit, which means that they want to cram more bits inside a given area. And they've been successful at it, but it's becoming harder, as you can see. It's not increasing as fast. What about memory bandwidth? We're looking at a single DRAM chip, basically. How much has it improved over the last 18 years? Yes?
4 times.
4 times. Any other takers? I'll give you the curve. It's about 20x. But DRAM bandwidth is also limited by the pins, as you mentioned. DRAM chip is also limited by the pins. And this is not the real design point that most manufacturers have. And this is the DDR technology. Actually, some technologies have higher bandwidth, but it's not improving as fast as capacity. What about latency? Any takers on this one? 50 times? You're very optimistic. I wish. I'll give you the curve over here. This is real data. It's 30% actually. Actually, I thought this was smaller than that, but 30% is the real. So basically, latency has not improved as much. And this is becoming a bigger bottleneck going forward. We're looking at techniques to reduce memory latency, DRAM latency in particular. I'm not going to talk about those. But yeah, these are the trends that we have today. But DRAM is actually very critical for performance. These are some, in my opinion, I don't want to call them backward-looking applications, but the applications that we know of much better than applications that don't exist yet. And many people have documented that memory is a big performance bottleneck in all of these applications. And we've been, I'm going to talk about this work later, but we've been looking at more mobile applications as well and analyzing them. And we also see that memory is a big bottleneck in the mobile applications also. Not only a performance bottleneck, but also an energy bottleneck. So that brings me to the next point. Energy in memory is a key system design concern today. Energy in general is a key system design concern, but the memory energy is growing. This is beautiful data from IBM's Big Iron servers. Charles Lafergie and others basically wrote a paper in 2003 examining IBM's Big Iron system. And they said more than 40 to 50% of the entire system energy in this Big Iron system is spent on the off-chip memory hierarchy. At that time, the off-chip memory hierarchy consisted of DRAM, off-chip storage, off-chip caches, off-chip interconnect. Now fast forward about 10 years, let's say, same folks, roughly, wrote a paper on IBM Power 7 and analyzed the power consumption of IBM Power 7. They said basically more than 40% of the system power is just in DRAM. Of course, a lot of things became on-chip
So
during
they
that time.
include the disk or just the DRAM?
Yeah, just the DRAM in this case, yes, according to their results. Maybe the studies are not perfectly comparable.
So if you had the disk, I mean, that's consume a lot of energy too.
So it depends on the applications. I agree with you. If your applications are very much disk-bound, that consumes a lot of energy. But also, I believe they looked at a lot of memory-bound applications in this work. There are also studies from GPUs that also show very similar results. More than 40% of the power is in DRAM. And DRAM consumes power when it's not used also. You need to periodically refresh it. And that's not very good as a technology. And this also turns out to be a scaling problem. So we've actually recently analyzed some of these workloads that I mentioned earlier, and we found that more than 60% of the total system energy in these consumer workloads from Google are spent on data moment. Again, I'm going to get back to this. So data moment is actually a fundamental bottleneck because of the pins and also because of the way we design the systems. So on top of all of this, DRAM technology scaling is becoming more difficult. Ending may be a strong word, but when I gave this talk, not this talk, but a version of this talk about 5 years ago in the memory conference, Samsung's vice president, Bob Brennan, also gave a talk right after me, or right before me, saying the same thing. DRAM technology scaling is ending. And I believe this is true. It's not becoming easier for sure, it's becoming much worse. So what is technology scaling? Essentially, the feature size of a DRAM cell, we're able to reduce it every technology generation. And that feature size, let's call it X, that will not scale easily below X nanometers. And people have been projecting changing that X. And I don't want to change my slide when they change that X, so I don't want to keep my slides coherent with their projections. So let's keep that as X. I'm going to get back to that later. But reducing the size of the DRAM cell clearly provided many benefits. Higher capacity density, that was the major goal, but it also led to lower cost and lower energy consumption also. If this goes away, then we're going to have a big difficulty satisfying these requirements up here. So let's take a look at the scaling problem a little bit. I'm going to motivate intelligent memory controllers, especially because of the scaling problem to begin with. So there are increasing difficulties we're going to get into. And people have proposed emerging memory technologies for this, actually. Not just for scaling, but for other reasons as well. So there are 3D stacked DRAM, for example, that provides higher bandwidth, reduced latency DRAM, low power DRAM, and non-volatile memory, which are very promising. There are many different types of non-volatile memory. And if you look at these technologies, they all have some greens. These are the most salient greens, in my opinion. But unfortunately, they also have some reds. And these are some of the most salient reds. As a result, people have been looking at, researchers and also designers have been looking at hybrid memory technologies that look like this. You have multiple different technologies, and you combine these different technologies such that they have complementary greens, hopefully, and complementary reds. And you design the hardware and the software to manage the data allocation and movement such that you can exercise the greens as much as possible while avoiding the reds as much as possible. And that's the idea, and this is already happening. It's going to happen increasingly more, in my opinion. But if you look at if you design a system like this, then you definitely need intelligent controllers, because you need to actually move the data between these two different technologies. And if you don't have an intelligent controller that understands, at least in a minimal way, the characteristics of that data, for example, what's hot, what's not, and what is written to a lot and what is not written to a lot, and then understands the technologies such that it can map the data in an intelligent way, then it's going to be very difficult to manage this. And this is already happening also. So this is my first point where I motivate the intelligent controls. I'm going to motivate that more as we build up into processing in memory in this talk. So it's not just us, it's not just the academics. Industry is writing papers about it too. This is one of my favorites. It's written by two companies that don't normally talk to each other, but Samsung and Intel actually wrote this paper together where they said DRAM process scaling is getting much more difficult. Refresh is a problem, as we've discussed briefly. I'm going to go into this a little bit more detail later on. And a good solution direction is having a slightly intelligent memory controller. Basically, controller does some of the work to actually enhance the deficiencies of DRAM. And this is also a paper where they proposed error correcting codes inside the DRAM chips If you actually went to a DRAM manufacturer maybe 10 years ago and said, I want error correcting codes inside your DRAM chip so that my memory is more reliable, they would kick you out of the room probably. But they're actually having DRAM chips with error correcting codes right now. Going forward, all of the LPDDR chips have error correcting codes in them. And we have some studies with those chips that I'd be happy to talk about separately. So clearly, an intelligent memory controller can overcome some of the deficiencies of this technology. And I'll talk about that in a little bit also. So this is the agenda of the talk. I'll talk a little bit more about the need for intelligent memory controllers. And I'm going to motivate this from bottom up. There's a huge push from circuits and devices, in my opinion. Technology scaling is becoming much harder. So it's very difficult to solve the technology scaling issues in the device and circuit level. So having an intelligent memory controller can overcome some of those deficiencies. And also there's a huge push from top down, or pull from top down. Essentially systems and applications are pulling us to do more inside the memory controller such that we can process the data in a much more efficient way. And in my opinion, we're stuck in this middle where we actually need to do something inside the memory controller in a smart way. And then I'm going to talk about processing in memory, hopefully give you 2 different flavors of it. And then I don't think we're going to have time to talk about adoption issues, and we'll conclude. Does that sound good? Okay, so let's do the bottom up, but I'm going to start with something totally different. Does anybody know who this person is? I think there's information leakage on this slide, so. This is Abraham Maslow. He's a very famous American psychologist. He actually dedicated his life to understand why people do the things they do. And he's written a book which you find over time. He's probably more famous for this hierarchy of needs. Basically, he came up with this hierarchy of needs, essentially where he said if you actually don't have your safety and physiological needs satisfied, you don't really care about very abstract forms of art. So there's a hierarchy here. So that's why I think we need to start with reliability and security. If you don't have a computing system that is reliable and secure, then maybe you don't really care about what else we do with this system. And I also use this picture in my class especially to motivate issues related to reliability and security, especially the intersection of them. If you have an unreliable system, this could affect your safety and security. Does anybody know where this bridge is?
Tacoma.
Yes, it's the Tacoma Narrows Bridge. Are you from there?
Portland.
Oh, okay, that's good. Yeah. That's a bridge that I never crossed because what happened to this bridge was this in 1940. Essentially, because of aerostatic flutter, the bridge collapsed. And actually, if you go there right now, there are 2 bridges. So redundancy principles are at work. You can cross those 2 bridges which replaced this. I think this is an example of a reliability problem that's actually affecting safety and security. In this case, the only fatality was a dog that was stuck inside a car. The professor from Washington State actually was trying to save that dog, but he wasn't successful. But we'll get back. I actually liken the DRAM scaling problem to this, and a lot of the security problems to this. You have a reliability problem that's really affecting our security and safety today. It's another example that I like using to motivate these issues. So these people are very happy right now, but a minute later, if there's a bit flip over here, they may all fall down. So I think security is actually about preventing unforeseen consequences. It's a very general definition. But we should be thinking about those unforeseen consequences when we're designing the systems that we're designing going forward. So how does this relate to DRAM scaling? Basically, today we're having DRAM scaling issues that are affecting the reliability of the circuits in a way that's really affecting the security and safety. So let's go back to the fundamentals of DRAM. If you look at DRAM, like any other memory technology, it needs a storage device and it needs an access device. In DRAM, the storage device is the capacitor, and the access device is the access transistor, bit line, and the sense amplifier, basically external circuitry that enables you to access this capacitor. And for this technology to work, this capacitor must be large enough for reliable sensing, and this access transistor must be large enough for low leakage and high retention time. And this was the value that was assigned to X by ITRS, the International Technology Roadmap of Semiconductors, in 2009. They said reducing the size of the circuit below a feature size of 35 nanometers is challenging. And they said we would reach 35 nanometers in 2013. Clearly, we're actually below 35 nanometers today. Does anybody know what is the feature size of a DRAM cell in the cutting-edge DRAM chips? Any guesses? 12? 14? Getting closer. So we're actually around 17 nanometers right now. And I think the path is clear for probably 12 nanometers. And I like asking this question when I visit memory companies, Samsung, for example, Hynix. What do you think is the limit of technology scaling in DRAM? Usually I get the answer 7. I think that's optimistic. We'll see if we reach that. But clearly, this has come. Certainly, it was challenging to reach 17 nanometers, but we reached it. But this actually has come at a cost. I'll give you some examples of the cost. Basically, we've done this study with Facebook a few years back. We've analyzed all of the memory errors that they encountered and logged in their system. And they have a lot of memory in their system. They have a lot of servers. They don't allow us to report how much memory and how many servers they have because this apparently affects their stock price. They're fearful of that. Or maybe they should be fearful of other stock price effects. But if you actually analyze that data, you see that there is a positive correlation between the chip density that's used in a server and the error rate that you observe in the server. I don't want to go into the detail of how we actually do this. This is a correlational study. You cannot infer causation because we don't control the system that's operating in the data center. But clearly there's a very strong correlation between the density of the DRAM chip and the error rate that you see in the servers. And this is actually becoming worse going forward.
So,
yes.
When you say security, you mean you sort of mean reliability?
I'll get back to that. I actually mean security, but we'll get to that. So reliability issues will cause security problems. But give me some more time. Okay. So there are actually a lot of interesting things over here. We're analyzing some more data. I'd be happy to talk about it, but I don't intend to go into this paper in more detail. So we've also been doing more lower level studies. We built these infrastructures where these are actually FPGA-based memory controllers where we could plug in DRAM and test the DRAM. And we wanted to study scaling issues. Basically, we wanted to study DRAM retention time issues first. I'm going to talk about that briefly. So this is one of the infrastructures that we built. We can actually heat DRAM and then measure the effects that we have and understand. We actually released this FPGA-based infrastructure recently in an HPCA paper. We're happy to support it. It is actually relatively easy to use. It's C++ programmable. You could actually test DRAM, change the latencies, change the refresh retention time, and it's open source. And one of the things that we've been studying is, for example, refresh. Today, we refresh every single DRAM cell every 64 milliseconds. At high temperatures, it's every 32 milliseconds, and the next generation is actually going to be every 32 milliseconds to begin with. So refresh is becoming an increasing problem. But this doesn't have to be so. If you look at the DRAM, the retention time profile of a DRAM chip looks like essentially this. Because of process variation, manufacturing process variation, there are some weak cells, there are some strong cells. Today, we're designing systems such that we're actually refreshing everything based on the refresh that is required by the weak cells. But if you had slightly more intelligent memory controllers, we could figure this out. Basically, the memory controller can profile the system once in a while and understand how often you need to refresh which cell based on the strength and the weakness of the different cells. And if you do that, actually, it turns out you can cut the refresh rate, if you look at this picture, by almost 75% in this case, and get rid of a lot of the energy consumption, idle time energy consumption. Of course, it's not that easy. Your memory controller needs to be intelligent because the refresh rate, retention time of a DRAM cell depend on its location. It's dependent on the stored value pattern in the DRAM cell and around the DRAM cells around it. And it's also dependent on time. This is very unfortunate, actually. That makes this very complicated. There's this variable retention time phenomenon that's also present in the Samsung and Intel paper, where charge gets trapped randomly in the access transistor, and you cannot predict this process. I call this a quantum-like effect. Essentially, at this time, if you test DRAM, the retention time of the cell is, let's say, 100 seconds. But 100 seconds later, when you test that cell, the retention time could be 8 milliseconds. Because charge may have gotten trapped in the access transistor, and once charge gets trapped, the leakage is much faster through that path. Because of this, you need an intelligent memory controller to actually adapt your refresh rate. And you do need error correcting codes in DRAM to handle that effect. Okay, this is very interesting, and I think this is one of the other reasons why we may need intelligent memory controllers to handle technology scaling issues like refresh, like this. And this actually enables other things, in my opinion. If you actually have an intelligent memory controller that figures this out, that exposes the operating system, you could actually play a lot of tricks in terms of how you allocate your data structures into memory. None of these interfaces exist today, so unfortunately, this is probably going to take a long time to happen. But I think that there's a lot of hope in terms of research to understand these issues. In the memory controller, you can do this currently, and I'd be happy to share some papers. But while we were doing studies like this, we wanted to understand the retention time problem because it's really fundamental to DRAM. If you actually think about the scaling issues with DRAM, refresh is at the heart of it. If you talk to an insightful DRAM designer, they will tell you retention time is a scaling issue with DRAM. We do not know what is the retention time of a DRAM cell, basically. Okay, but with an intelligent memory controller, you can figure out. While actually we were doing these studies, we also stumbled upon something else in DRAM, which is even worse, in my opinion. And this is essentially, you can predictably induce errors in most DRAM memory chips. This is called the row hammer problem. Essentially, it's very similar to that bridge, in my opinion. It's a simple hardware failure mechanism that can create a widespread system security vulnerability. And I like this Wired article, which is really getting the title right, in my opinion. He says, forget software, now hackers are exploiting physics to create security vulnerabilities. And I'll talk about the problem. This is actually very fundamental to all of memory. It just so happens that it got exposed to DRAM, and it slipped into the field. And it happens in all kinds of memory. So let's take a look at the problem. Memory consists of rows. And in DRAM, if you want to read a row, read some data, you need to activate that row. Basically apply high voltage to that word line. Now if you want to read another row, you need to close this row by applying low voltage to that word line. This is called precharge in DRAM. Now if you do this repeatedly, read a row many, many times, activate precharge, activate precharge, activate precharge, activate precharge, activate precharge, it turns out in modern DRAM chips, some of the cells in adjacent rows get flipped from 1 to 0 or 0 to 1, depending on the encoding. And we call this the hammered row. We call these the victim rows. And we showed that you could actually see this effect in most real DRAM chips you can buy today. Today meaning as of 2014. And we tested chips from 3 major manufacturers. Unfortunately, there are only 3 major manufacturers in DRAM today. It's an expensive process. And we saw that more than 80% of the modules we've tested for each of the manufacturers actually is vulnerable to this effect. And it's a scaling problem because this effect didn't occur in chips that we tested that were manufactured before 2010. The first occurrence happens in 2010. And essentially all of the chips that were manufactured between 2013 and 2012 are vulnerable. So let's go, before we talk about more, let's talk about why it's happening. This is happening because DRAM cells are too close to each other. Essentially, there's electromagnetic coupling between them. And whenever you're activating one row, there are multiple reasons actually. It's a combination of multiple reasons. But one of the most intuitive reasons is electromagnetic coupling. Whenever you activate a word line, you're slightly activating the word line that is adjacent to it because they're not isolated enough. And when you activate the word line that's adjacent to it, you're essentially opening the cells, and you're leaking charge very little. And if you do this activation many, many times, let's say 10,000 or 20,000 times, before the cells get refreshed, it turns out you slightly activate adjacent word lines and deplete the charge from some of the vulnerable cells. So one solution to this is actually refresh cells more frequently, all of memory more frequently, such that you cannot do it enough times. You cannot do these activations enough times such that you deplete charge from adjacent rows. That may not be a good solution because that actually increases your refresh rate that we're trying to get rid of, actually. So the cells are essentially too close to each other. But what is worse is if you actually have these bit flips exposed in your main memory, now you can write programs at the user level that can exercise this. This is the program that we wrote in our ISCA 2014 paper. This is the 6 lines of x86 code. Basically what this program does is it selects addresses x and y such that they map to the same bank in memory. And it avoids cache hits to x and y, and avoids row hits to x and y. Basically what it does, it ping-pongs accesses to these rows x and y. And if the chip is vulnerable, it will find the bit flips. Later, actually, we realized that you could select x and y such that you could sandwich a row in between. And Google actually made this attack much more powerful by selecting those addresses such that you could do this double-sided row hammering, if you will. Because if you actually select a row over here and hammer the adjacent, select the addresses x and y such that they're adjacent to that row, you could actually do this double-sided row hammering. Okay, so these were results from our paper. Basically showed that if your memory controller is fast enough to do these activates, you can actually induce errors in real systems. These are real system results. There's nothing special about Intel and AMD. Real system, actually all of manufacturers have memory controllers that are very good, that are capable of inducing these errors. And I'll give you examples from other people's works. So when we actually did these studies, we were very concerned about security. And the first sentence we wrote in the paper was, memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. And I still believe this. This is very fundamental. And we said that you could actually construct an attack that could hijack a system or do any kind of data corruption, if you will. And while we were working on it, the good folks at Google Project Zero actually took advantage of it. And essentially, they showed that you could use this row hammer mechanism. They called the bug. I like calling it a failure mechanism to gain kernel privileges. This is directly from their blog post online. They basically figured out the problem from our paper. They tested a selection of laptops, and they found that the laptops are vulnerable to row hammer. And they actually built 2 working privilege escalation exploits. If you're interested in security, I would definitely recommend reading this blog post. It's beautiful, beautiful security engineering. One exploit is not that interesting. It takes over the Google native client. But the second exploit is very powerful, which was the basis of many other works that built on this. Essentially, they use these row hammer-induced bit flips to gain kernel privileges on x86-64 Linux with a user-level process. What they were able to do with beautiful security engineering is to induce bit flips on the page table entries of a process, where the page table entry points to the page table of the process. And if you actually are able to do that, you could gain essentially write access to your own page table. And once you have write access to your own page table, all of the security guarantees are compromised. Essentially, that single bit flip in that bridge enables the collapse of the bridge. And it's beautiful. It's not that easy, of course. You can think of this as flipping the write enable bit into the page table entry that points to your own page table. But of course, targeting a single write enable bit is very low probability, so they did actually very beautiful security engineering to increase the probability of the attack. It's a probabilistic attack in the end. And people actually start drawing pictures like this. I like this picture. Is it the end of memory? And they're actually really insightful things on Twitter. I like this particular characterization that says it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door that you were really after. This is from a famous hacker somewhere on Twitter. Okay, so they're actually really interesting works that built upon this later on. This is, I'll give you an example of some of these. I'm not going to go into the detail. This one shows that you could actually, yes?
I wonder if it is possible for the data manufacturers to basically prevent these kinds of activities simply by closing the row hammer.
So we'll talk about the solutions. Give me a couple of minutes until I build up to that. I think so, yes. But we'll talk about that. Although I'll say I think so with a caveat. Okay.
The TLB problem exists not only in the case where you could have a shared TLB among multiple threads. It could also be present in a system in which the TLB is private to a thread, right? That's what you say. Because a particular user, a particular process could take control.
Exactly, yes. So because your physical memory is actually, you could actually hammer, essentially you change the permissions of your own process, and then you gain access to the entire system.
I thought it was only with a multi-threaded system.
No, it's actually, yeah. So this work showed, for example, that you could induce these attacks through JavaScript in a remote server, and you could take over a remote server. This one is actually very interesting. Basically, this one showed that in the Android operating system, the operating system allocates pages in a particular way, in a predictable manner. And they were able to fool the operating system. They were able to figure out which part of the memory is vulnerable to row hammer and fool the operating system to allocate a page table entry for your own process at a location that they knew was vulnerable to row hammer. So they were able to deterministically take over Android machines. And they used to have an application that you could download. If you have an Android phone, you could test if this is still available and get compromised if you're interested. This is work from Vrije University in Amsterdam. And similar folks, same group actually showed that you could do these attacks through the GPU with the massive parallelism in the GPU and essentially escalate your privilege through the WebGL interface, take over the system. And again, similar folks showed that you could do these attacks over the RDMA, Remote Direct Memory Access Interface. These are relatively recent ones in May 2018. And some other folks also showed that in TU grads. These are the folks who were actually involved in Spectre as well. They showed that you could actually take over the system. So maybe this is one potential solution before we get to the DRAM manufacturers and another security risk. Okay, so what are the solutions? Let's talk about that. If you're vulnerable in the field, there are many DRAM chips that are out there in the field that are vulnerable. And the solution that makes sense is to actually increase the refresh rates across the board. And that's essentially what the manufacturers did. Apple is nice because they actually put out a clear description of it. They didn't tell you exactly how much they increase the memory refresh rates by, but they said that it's, I believe it's about 2x or so.
What's the corresponding energy?
Yeah, it depends on the application, of course, but it's not very nice. So today, refresh consumes about, let's say, between 5 to 20% of the system energy. It doubles, essentially. Not so good. And this doesn't necessarily get rid of all of the errors, in my opinion. So in our paper, we showed that you need to, if you want to get rid of every single error that we saw in the chips, you need to increase your memory refresh rate by 7x, which is not good. We don't want to do this across the board refresh rate increase. And I believe this exists because the memory controllers are not programmable enough today. They are programmable enough to increase the memory refresh rates. So our solution was actually more cooperative solution between the memory controller and the DRAM. It's called probabilistic adjacent row activation. Essentially, the idea is very simple. Whenever the memory controller closes a row, it decides whether or not it refreshes the adjacent rows, only the adjacent rows, activates the adjacent rows with a low probability. And the probability could be 5 out of 1,000 times, for example. And it could adjust that probability either dynamically or statically. And we saw that you could actually get a very good reliability guarantee that's much better than hard disk reliability guarantee in the system. And if you're not comfortable with the value of P that you choose, you could actually increase that. Essentially, this refresh is only the adjacent rows, so the overhead of this is very low. And we quantified the overhead. If you're interested, you can read the paper. It's also stateless. It's low cost and low complexity. I don't believe it needs to be random, but we actually looked at random. But we actually have a solution of generating random numbers inside the DRAM today. I'd be happy to talk about that separately. So randomness is not a problem also. So I believe it's an effective solution. Yes?
Since the core problem is due to the density, increased density, has anyone looked at perhaps using redundancy in the sense of not using all the rows
Sure.
at a given time? If you get what I'm trying to say, maybe in some way trading off some of the actual density.
Density, yeah. So maybe having error correcting codes, for example.
Correct.
Yes. So I believe error correcting codes are one potential solution. Actually, we examined error correcting codes. The paper shows that you sometimes get as many as 4-bit flips. So your error correcting codes need to be strong enough to cover for that case. I think that's one potential solution that's reasonable, that already exists, but I don't think it's going to cover all cases. And I believe it's not a very efficient solution for this particular problem because it's a very access pattern dependent failure mechanism. You can actually be much more efficient with a solution that's like this, for example, or trying to detect these patterns. So what are the requirements for implementing something like pair? Actually, this is already done. Some form of it is already done in DRAM chips today. It doesn't always work, in my opinion. For example, you could exploit the slack and timing parameters in DRAM chips. Then manufacturers are already doing that. The timing parameters are defined such that there's slack in them. So the refresh cycle, for example, has some slack such that you could sneak in extra refreshes in DRAM. And manufacturers are using that to sneak in some extra refreshes to prevent some of these errors. Does it always work? Don't ask me. So basically, there's plenty of slack, and we actually used our infrastructure to analyze that slack. I will argue that this is not a good solution because we want to actually get rid of that slack. That slack is there because of huge process variation across the chips and within a chip. If you actually get rid of a lot of that slack, you can reduce the latencies in your DRAM chip quite a bit. And we want to get rid of the latency in memory. So I believe a better solution is really doing this inside the memory controller. And DRAM manufacturers have very little room to maneuver. And we cover actually 6 other solutions in the paper that I'm not going to talk about. But if you actually have it in the memory controller, you need to have better coordination between your memory controller and DRAM. So your memory controller, for example, needs to know which rows are adjacent to each other in DRAM. And this is information that you don't know, unfortunately, today, because there's so much disparity in the disconnect between in the communication between the DRAM chip and the memory controller. But if you know that, then this is a very easy problem to solve. In my opinion, this is not a very hard problem to solve, actually. But there is good news, I think. This is a relatively recent memory controller released by Intel that's exposed to the BIOS. It's not exactly what we envisioned, but it's going along those lines. Essentially, in the BIOS, you can pick between hardware row hammer protection or 2x refresh. And hardware row hammer protection essentially means that row hammer activation probability. It's probabilistic adjacent row activation. And you can basically pick your probability. You can say every other activate, I want to activate the adjacent rows, or every 512th activate, I want to activate the adjacent rows. So I think things are going in the right direction. Memory controllers are becoming slightly more intelligent, as you can see. But we don't want to do it in BIOS. We want to do it actually while the system is operating, in my opinion. You want to be able to adapt to these errors. Okay, if you're interested more, there's more detail. And I recently written this paper that talks about some of the other upcoming issues. And as I said, industry is writing papers about similar issues. They didn't talk about the row hammer problem in this work because that was not exposed at the time when they wrote this paper. But there are other problems related to this. And the solution direction, I believe, that's proposed by the DRAM controller team at Intel and the DRAM circuit design team at Samsung is toward the lines that I've been motivating so far. And I'll motivate a little bit more. We already know how to design some of these controllers. We actually design NAND flash controllers that are much, much more sophisticated than DRAM controllers. And NAND flash is a technology that has a lot of deficiencies. And we designed the controllers to have very strong error correcting codes, adapt to the voltages, and try to minimize the error rates. I'd be happy to talk about that separately, but we recently written a long paper that talks about what is done in flash memory-based solid-state drives today. I believe DRAM controllers are going to look more like this. Of course, not to this extent, because flash memory has very long latencies, and we can actually design a lot of these mechanisms in flash memory such that you can take advantage of those long latencies. Whereas in DRAM, we need to act quickly, essentially. So I think hopefully the takeaway in this circuit scaling side is we need intelligent memory controllers to overcome the circuit scaling issues that we're having with DRAM. Let me motivate the top down a little bit. I motivated this earlier to begin with an application, and we're going to look into this a little bit more. Any questions so far? Okay.
So
I could talk about row hammer much longer, but
today they're already quite complex, right? I mean, they are just for performance reasons, especially in the core environment.
yeah. I would argue that they're not complex enough, but I agree. They're complex. They're because they need to deal with a lot of different latency parameters. They need to do scheduling. They need to do power management. I agree with you. They're already complex. It's not easy to design a memory controller. But I think we need to separate the correctness concerns with some of these other concerns, performance concerns. But they're also very important because everything goes through the memory controller in a system like this. Okay, so let's talk about the system trends. I believe there are three major trends. Data access is a major bottleneck. Today, applications are increasing data hungry. Energy consumption is a key limiter. And data moment energy dominates compute. I'm going to give you examples of this relatively quickly. And this is especially true for off-chip to on-chip movement. Clearly, we need more memory performance. There are many applications like this. And I think in my mind, the question is like this. Do we want a future that looks like this? Or do we want a future that looks like this? I would probably pick the previous one. And I will also deconstruct what I said earlier. Maslow actually didn't say that safety is the most important thing. He actually said physiological needs are more important than your safety. So if you're actually about to die, maybe you don't care about your safety or security, right? Of course, that's a joke over here. But so clearly, we want a future that's high performance, energy efficient, and sustainable. But the problem is, even though data access is the major performance and energy bottleneck, our current design principles cause great energy waste. Exactly go against this bottleneck. And they also cause great performance loss. I put this in parentheses because we actually do a lot to overcome that performance loss. We build a lot of mechanisms, hierarchies, prefetching, multi-threading. They're all there to reduce the performance loss, but they all add to the energy waste on top of that. So they clearly create a trade-off between them. And they make the energy waste much worse. And the fundamental problem is processing of data is performed far away from the data. We're just moving data too much. And if you go back to 70 years ago, this is von Neumann's fundamental paper, where he defined three key components of a system: computation, communication, storage, and memory. And if you look at the history of computing, for a long time, we've heavily optimized this computing unit. And I take this generally, computing unit includes the accelerators that we have today also, not just the general purpose computers, general purpose CPUs. We're overwhelmingly processor-centric. All data is processed here at great system cost. And this is heavily optimized and is considered the master, whereas the data storage units over here are dumb and largely unoptimized. Only the ones that are inside the computing units are very optimized. Yet, we have a problem. This is Dick Seitz. He wrote this one-pager in Microprocessor Report in 1996, where basically he said, we designed this alpha processor that is supposed to retire 4 instructions per cycle, but it's finishing 1 instructions every 4 cycles. Why? Because it's waiting for memory. And he actually, it's a very insightful one-pager if you're interested in reading it. He basically says, future processor design should just focus on memory systems.
I would argue it's a poor design.
Sure. You could argue that also. But this is true actually for many things. I'm going to motivate this. Give me some more seconds. So this is 1990s. Fast forward 10 years later, this is my own PhD thesis on run-ahead execution. We analyzed the workloads that Intel used to design their processor with at the time. We basically saw the same thing, essentially. The processor is waiting most of the time for data to come back from memory. Okay, if you don't believe this, fast forward 10 more years. This is Google's paper in ISCA 2015, where they essentially show the same thing. They basically look at, according to them, all of their data center workloads and classify the microarchitectural bottlenecks. They basically say processor is waiting for the backend to return the data, and it's doing useful work only 10 to 20% of its time. And they're actually very interesting analysis. They basically show that their workloads are much more intensive than some of the spec workloads that people are using in general. Okay, so they go into more detail. So basically, over the course of 20 years, nothing has changed. Of course, processors have become more powerful, but they're still waiting for data to come back from memory. So I believe we have a grossly imbalanced system. Processing is done only in one place. Everything else just stores and moves data. As a result, data moves a lot. This is energy inefficient, low performance, and complex. And if you want to actually overcome the performance effects of this, we design overly complex and bloated processors and accelerators to tolerate data access from memory. We design complex hierarchies and mechanisms. That leads to more energy inefficiency. And that essentially takes away from other ways of improving performance, and that increases the complexity in the system. And as a result, we have the picture that I showed you earlier. We have a system that looks like this, but most of the system, actually if you do the calculations, more than 90% of the system consists of caches, interconnects, memory, and controllers to control the data movement and storage. Computation is a very little part of the system. Let's take a look at the energy perspective very quickly. This is a slide that I borrowed from Bill Daly. We could argue with these numbers because this is a relatively old slide. Also, it depends on technology. But if you look at a 64-bit double precision floating point operation, it's about 20 picojoules according to these numbers. A DRAM read or write is about 3 orders of magnitude higher energy. And I'll take the liberty to make it 3 orders of magnitude. It's about 1,000x. If you go back 70 years ago and try to get these numbers, it was not like this. Essentially, this double precision floating point operation, or a complex addition, let's say, was 2 orders of magnitude worse than a memory access at that time. But this scaled really, really well. This didn't scale too well. As a result, we're 5 orders of magnitude on the other side right now. And if you don't believe that 3 orders of magnitude, there are a bunch of other studies that show that this is about 2 orders of magnitude. 3 orders, there's still there's a large disparity in the energy of a memory access and an add operation. Clearly, people are trying to reduce the memory access energy, but still, that interconnect is very energy hungry. And as a result, we get the result that I mentioned earlier. More than 60% of the total system energy in important workloads that we care about is spent on data movement because of this energy disparity. Basically, we do not want to move data, in my opinion, if you want to be truly energy efficient and sustainable. So what do we do? Essentially, in my opinion, we need a paradigm shift to enable computation with minimal data movement and compute where it makes sense, as opposed to restricting ourselves to compute only in the accelerator or the processor. And where it makes sense, in my opinion, is where the data resides or where the data moves through. Essentially, we want to make computing architectures more data-centric. So our goal is to do processing inside memory, but this is not restricted to memory. It could be processing inside the storage, processing inside the network, in the interconnect, and there are examples of this throughout history, clearly. But memory is a bit hard because this interface is relatively rigid today. So basically, we want to store important applications over here, and we want to be able to query memory. Essentially, we can treat this as a potentially distributed system. We can ask the memory question, can you do this function for me? If the memory says no, then we probably do it in some other way. If the memory says yes, then we send the function to the memory. And the memory returns the results, and then we can zone in on the results and then figure out what we're trying to do. So there are many, many questions in designing a system like this. I'm not going to cover all of them in this talk. I'm going to give you some examples. How do we design the compute-capable memory and the controllers? Where do we do the computation exactly? Do we do it inside the DRAM cells? Do we do it close to the DRAM cells? Do we do it in the controller? And I will argue that we'd like to enable all of them, and then we'd like to be able to somehow enable the programmability of it, so adoption challenges are going to be related to that. How do we design the processor chip and the in-memory units? And how do we design software and hardware interface to enable this? Because none of these exist at this point. How do you design the system software and the languages and the algorithms? So Michelle is thinking right now, okay, this is huge. I agree that it's huge, but it's important also. Essentially, it's a across the stack problem, and we need to tackle issues across the stack to be able to enable something like this. But I don't believe there's an easy solution at any part of the stack in a general purpose way, at least. So far, we've talked about the push from technology, and industry is also open to memory architectures today. There are actually very interesting proposals that are going to come going into the future also, but also in the past, people are putting error correcting codes inside DRAM. Yes?
If we go back to the previous slide, so that would this preclude a system in which the chip would have multiple cores, for example, or accessing main memory?
No, I don't think so. I think this is fine. You could potentially...
so you're going to have multi-threaded controllers in there?
Potentially, yes. I'll give you an example of this later on. Not necessarily inside the memory chip, in my opinion, but very interestingly, people are looking at putting things inside the memory chip also at extra cost. But I believe you could have it with 3D stack technologies, for example, under the logic, in the logic layer of a 3D stack technology, you could have a multi-thread processor. I'm going to give you an example of this later on. Okay, so industry is basically looking into 3D stacked architecture. Some of these already exist, high bandwidth memory in GPUs. It's not used in a 3D stacked manner, but it could be used in a 3D stacked manner. And this enables high bandwidth. I'm going to talk about this later on. And people are also experimenting with things like automata processing, where you could do deterministic finite automaton computation inside the robuffers of a DRAM chip. This is actually processing inside the robuffer. And there are experimental processors out there. This wasn't the case 10 years ago. And there's a huge pull from systems and applications that we talked about, though. That's the summary of the previous part of the talk. Now let's go into how can we do this. And I'm going to give you two possible directions. It's not just two possible directions. These are two possible directions that we're working on. I believe actually increasing costs and power of a DRAM chip a little bit more by doing more processing inside the memory chip, maybe not minimally changing memory chip, is also interesting. So I'm going to talk about minimally changing memory chips. This surprisingly has not been explored as much in the past. And I'm going to talk about exploiting 3D stacked memory that is already available, I think. So the first realization is that memory, I'm going to give you examples from DRAM, but actually this is true for any type of memory. Memory has great capability to perform bulk data movement and computation internally with very small changes internally. So we can exploit internal connectivity in memory to move data, and we can exploit analog computation capability due to charge sharing in DRAM. I'm going to give you some examples. Let's start simple. Let's not even talk about computation, but talk about data copy and initialization. If you look at data copy and initialization, it's used in many applications today. It's a fundamental primitive, I think. And Google, in their paper that I mentioned earlier, showed that 5% of their cycles in the data center is spent in these two system calls. Not even general data movement, just these two system calls, memmove and memcopy. They call this as part of the data center tax. So how do we do data movement and initialization today? Initialization is a special case of data movement. Basically, if you want to copy a source page to a destination page today, you have to go through the processor, or at least the memory controller. You bring the source page byte by byte all the way into the L1, and the destination all the way into the L1, do the copy, and then write back the destination. It's high latency, high bandwidth utilization on a very important resource. It causes cache pollution, but you could eliminate that by setting up this through the DMA engine and not disturbing the caches. And it causes a lot of unwanted data movement. So if you look at a 4 kilobyte page copy through the DMA engine, not even going through the cache hierarchy, with some technology assumptions, DDR3, it takes about 1,000 nanoseconds and 3.6 microjoules. Now, wouldn't it be nice if we actually had the option to tell the memory, please do this, and don't bother anything else in the system, like this. This will be low latency, no bandwidth utilization actually over here, no cache pollution, but you could fix that today also, no unwanted data movement. And I'm going to show you an example in that in the best case that it reduces that 1,000 nanoseconds to 90 nanoseconds. Actually, you could optimize that to be 70 nanoseconds also. 3.69 microjoules to 0.04 microjoules. And the basic idea is very simple. We're going to exploit the internal connectivity of the cells in a memory array. In the best case, the source page and the destination page are in 2 rows that are connected to the same row buffer, sense amplifiers. And the idea is to activate the source page first, which brings the data into the row buffer. Now the data is very strong, amplified. If you look at a single sense amplifier, it actually is 100 times the size of a single DRAM cell. Now you have the data strong over here. Now we want to put the data to a destination page. How do we do that? We essentially activate the destination page, which implicitly deactivates the source page and connects the sense amplifiers or the row buffer to the destination page. We essentially use the row buffer as a temporary storage to move data from the source page to the destination page. That's the idea. Of course, there are a lot of other issues that I'm not going to go into, like the granularity. Is this really 4 kilobytes? Is it 16 kilobytes? Those are system level adoption issues that I'd be happy to talk about separately. But you could do this with minimal changes to the DRAM. It's really 2 consecutive activates, and almost all of the circuitry exists already. It's negligible hardware cost. If you want to do this across the subarrays and across banks, you need to add a little bit more logic, especially across the subarrays if you want to do this fast, because the subarrays in a DRAM bank are not connected naturally, except through this really narrow bus, but it's doable. So if you do that, then you can actually reduce the latency of a page copy by about 11 to 12x, and more importantly, memory energy by about, for doing that copy by about 74x, in the best case again. But clearly, this is not the best case. If you want to achieve the best case, you need to map your data such that source page and the destination page are in the same subarray. But we don't have the interfaces to do that today because the operating system is not aware of subarrays today. Right? So there are a lot of system level issues that we need to solve to actually implement this in a general purpose manner. If you actually want to accelerate your application, and if the substrate exists, I think initially people will adopt it to accelerate their applications, not doing it maybe by designing their specialized operating systems for it, or not doing it through the operating system, but just doing it through their application. Right? Okay, so that's the idea of row clone. So I think this is the mentality that I would like to convey. Essentially, we have some things that we can do really well inside the memory, and maybe if we add those specialized computation capabilities to the memory, we can treat memory as an accelerator that's somewhat similar to all of the other accelerators that we design, except these accelerators are sitting on the wrong side of the memory bus, whereas memory is sitting on the right side of the memory bus. Okay, so let's talk about computation. I gave you, maybe I cheated a little bit, I gave you copying, and zeroing is an initial special case of copying. Actually, zeroing, if you're zeroing a huge database, for example, it takes a long time. If you do it through row clone, it takes a much shorter time, but I'm not going to go into the application right now. But we can also do AND, OR, NOT, and majority by exploiting analog computation capability. I'm going to give you the basic idea in a little bit, with a little bit more effort, of course. And the idea is activating multiple rows at the same time performs computation. And it leads to significant performance and energy improvements. And I'm going to give you the idea and some applications a little bit. I believe actually new memory technologies enable more opportunities. There are some recent papers that talk about doing something similar in emerging memory technologies like phase change memory and memristors as well. I think that's very, very interesting for sure. And these could actually enable even more because fundamentally DRAM is crippled in the sense that it really cannot, every read is destructive. Right? You have to move the data somewhere to operate on the data. Whereas these memory technologies, you don't have to move the data because the reads are not destructive. So I think there's a lot more to do over here. So let's take a look at it in the context of DRAM. Let's assume that we have these 3 rows. I'm going to show you only 1 bit over here, but you can imagine this extends to 8 kilobytes or 4 kilobytes. Essentially, if you had the primitive to activate 3 rows concurrently at the same time, assume an ideal circuit, what happens is, because of charge sharing, the result that you would get over here would be the bitwise majority of ABC. If at least 2 of these cells are charged, you would get the charge state on the bit line over here. If at least 2 of them are discharged, you would get the discharge state. Essentially, that's bitwise majority, which is really nice. Now you can do bitwise majority in your DRAM rows and across all of your DRAM subarrays. So that's actually a lot of parallelism, bitwise parallelism. But the realization is that you could rewrite this Boolean equation like this, and by controlling the value that you store in C, you could get the OR of A and B or AND of A and B. depending on what you put into C. Now we can have bitwise and bitwise OR inside the DRAM. Well, this is good, but this is not good enough perhaps, because AND and OR are not complete functionally. So we wanted to add a NOT inside it. NOT is not that easy to get. Yes?
So the previous solution is basically you have 1/3 the area overhead, basically for the C, the controlling pin that will tell you whether to do AND or OR. Right?
So what we do over here is we actually change the DRAM subarray a little bit such that you could do these on special rows in DRAM. So we don't actually enable this to be doable across all of the rows. So there's a special part of the DRAM subarray where you need to move the data over there to be able to do these operations. And moving the data is relatively cheap with row clone. Yeah. So we try to minimize the overheads. But there is overhead. It's not as cheap as row clone. Okay, so we wanted to add the NOT also. Actually, NOT, the complement of a row, already exists in the sense amplifier, but it's on the other side. It's on the part of the sense amplifier that's not connected to the subarray. So the idea is basically to take this complement of a value that you read and connect it back to a special row in DRAM. And if you do that, then you actually are able to capture the complement of a row inside DRAM. It's a little bit more overhead because you need to have the special row in DRAM. And we analyze that overhead inside the paper. It basically adds about 1% additional area to DRAM. And that's the idea. So we also analyze the performance of this. It turns out the throughput that you get in terms of bitwise operations is significant. Essentially, it's higher than the GPUs, CPUs, and even 3D stacked memory. Actually, if you do this on top of 3D stacked memory, you get even higher throughput. I'm not going to go into the detail of this, but energy benefits are even higher. Essentially, the energy of NOT reduces by 60x, and an OR reduced by 44x, and you could actually add more, essentially combine these operations and get even more bitwise operations. So these are exactly, these are simulation results. Although energy, you could get SPICE simulation results essentially.
So you have your tool to do that. You can modify. You have a DRAM simulator that you can introduce like logic in it and simulate the whole thing.
Exactly. Yes. Yes.
Is there a way to control, like, basically these circuits are based full 4 kilobytes or 16 kilobyte activation.
Yeah.
And generally, C programmers are not writing structures of that wide, usually words or maybe double words or something like that. So is it possible to make your long row buffers into, say,
Smaller.
16 byte values and do these operations?
Yeah. Maybe not structurally changing the row buffers, but if you actually are able to do these operations in a finer granularity, yes, and we have some works that are undergoing right now related to that. I think that's important to provide that flexible granularity. I agree with you in that sense. Although there are enough programs that could take advantage of this also. I'll give you some examples of those. But I agree with you. If you want to be more general purpose, you need that finer granularity. Okay, so this is a summary of the performance improvement. So let's take a look at applications. This is clearly not meant to be for every application. Actually, you could do any application. As long as you modify your algorithm and restructure your data, this is functionally complete. You could actually build anything on top of this, but it may not be very efficient, clearly. But there are some applications that map really well to this. And I'm going to give you some examples very quickly. The bitmap indices are an example. Some databases are actually reconstructed to do bitwise operations in parallel to the column scans. Microsoft has built this web search engine, essentially bitwise operations. The reason they actually built these databases and web search engines to do a lot of bitwise operations, to do the search and queries, is because they want to take advantage of GPUs and FPGAs later on, which are very good at bit-level parallelism. And this turns out it fits well to for our purposes also. But DNA sequence mapping also, an encryption algorithm that we're currently examining, are other examples. So bitmap indices are example. Basically, you could express your database at bitmaps, and when you're doing the query, for example, if you're searching for people who are within some age range, who go to USC, who make this amount of money, and who are from this part of the world, essentially those are a lot of bitwise operations. You do ANDs and ORs and comparisons using the bitmaps, and that leads to a lot of bitwise operations that are a very good fit for this sort of architecture. And we looked at queries using these bitmaps, And you get significant latency reduction if you actually map them to what we call ambit, essentially. That's the structure that we have. Of course, this comes at a cost. You have to modify your algorithm and how you actually do it. So it's not, you need to actually design your algorithm so that it fits ambit. This is a database that was designed by Jignesh Patel's group at University of Wisconsin, Bitweaving. They actually redesigned the database such that they could do the column scans very nicely on GPUs in a bitwise manner, and we actually were able to easily port this. Vivek did this, this was part of his thesis. And he showed that if you actually have this database ported to Ambit, you could get about 12x speed up in queries by Ambit. So there's significant benefit to be gained if your application is already doing a lot of bitwise operations, and you could port it to Ambit. I believe there's more, but I don't have time to cover more. So I think we have it. I'm going to cover the 3D stack in a little bit if you have time. I'll finish this part of the talk with the does memory have to be dumb. Essentially, we're designing DRAM chips as dumb devices. But does it really have to be the case going forward? I don't believe so. And I believe non-volatile memory technologies are a very good point to changing that mindset, because those actually open the field right now. Non-volatile memory technologies don't have 50 years of legacy design in them, so you could actually design them to be much smarter. This would force DRAM to be much smarter, in my opinion, also. Okay, let's switch gears a little bit and talk about 3D stacked memory, not minimally changing memory chips. So I think this is also very interesting. It's another way of doing processing in memory. And it's more opportunistic because 3D stacked logic and memory already exist for bandwidth reasons. Essentially, you have some logic layer over here and memory layers on top of that, and they're connected via some technology through silicon vias, are the current technology, so that they can, the memory layers can provide very high bandwidth to the logic layer at low latency. Of course, there are issues like thermal issues, which is true with any 3D architecture, which I'm not going to talk about as much here, but we can combine them. And I believe there are more interesting true 3D technologies that are under development. For example, if you use carbon nanotubes over here, that could be very interesting. There's work going on at Stanford related to that. I think this is going to be very, very interesting going into the future. And this is essentially 3D stacked memories are increasing since 2011 with wide I/O and HMC. And this is based on a paper that we've done in 2015. So there's more coming going forward. So when we first started looking into this, we had two key questions. We've elaborated on those. And the first question was, how can we accelerate important applications if you use 3D stacked memory as a coarse-grained accelerator? Architecture and programming model, what is it? And what are the mechanisms for acceleration? I'm going to talk about that. And we also wanted to look at minimal processing and memory support we can provide without changing the system significantly, without changing the programming model or virtual memory mechanisms, while achieving significant benefits. If you have time, I'll get to this. But let me talk about this one, because this shows a potential of processing in memory in a technology like 3D stacked memory first. And when we first started looking at this, we thought graph processing was important. I believe this is still a very, very important application, because graph processing application is not limited to this. There's a lot of graph processing that's done in bioinformatics right now. Genomes are represented as graphs going forward. In fact, it makes sense to represent them as graphs that are modifiable, because people have recently found out that because of the biases that are introduced in sequencing, human reference genome is actually missing more than 10% of it. I don't know if you heard that news, but people recently showed that we had actually 10% of the reference genome that we haven't sequenced, because we actually had a biased sample coming from the Europeans, if you will. So graph processing is actually very, very interesting, and it's growing. So Facebook, when I give this talk at Facebook, they like correcting me, saying that it's not 1.4 billion, it's 2.23 billion. But then I added the circa 2015, so that I don't need to change my slide again. Okay, so scalable large-scale graph processing is challenging. If you throw cores at it, you don't gain much, because it's actually a very much bandwidth bottleneck problem. I'm not going to go through this in detail, but this is page rank computation, and if you look at it, you have frequent random memory access and little amount of computation. This is an example application that exacerbates that energy bottleneck that we talk about, 3 orders of magnitude. Every time you want to access memory, you pay 3 orders of magnitude energy cost compared to the computation that you're doing, and because you don't have good locality, you're essentially bringing data that you're not reusing, and you're wasting all of that energy. So we designed a system that's called Tesseract. This is actually a system with a lot of components. I'm going to give you the key ideas relatively quickly. Essentially, it takes advantage of this 3D stack logic and memory. And inside the logic layer, it puts a multiprocessor, if you will. If you look at this 3D stack memory, it partitions the logic layer and the memory into what's called vaults. And each vault has a controller that controls the memory stack on top of it. And these controllers are connected to each other with some network. In this case, it's a crossbar, but you could actually look at network designs for this also. And they can communicate with each other. And basically what we added to this was a simple in-order core that could do computation. It's basically general purpose. It's not really specific to graph processing from that perspective. You could do anything inside this in-order core, but we use it for graph processing. Essentially, we connected these hybrid memory cube chips, or 3D stacked memory plus logic chips, with some other interconnect, with some other topology. It was Dragonfly in this case, but again, you could have other topologies so that you could scale up the system. And after that point, you map your graph on top of these chips, and then the vaults inside the chip. And then whenever you need to process a data element, essentially you send a message to that core that houses the data element to do the computation. You basically send messages to the computation on the data elements. You don't move the data. Data stays where it's put, mapped to begin with, at least in this system. And the idea is we changed the entire system. This looks kind of like a GPU some time ago. It's all physically addressed. It's non-cacheable. Basically, you offload the entire graph computation onto this system, and the graph computation happens, and then it keeps happening. It's a message passing based system. It can remind you of old message passing computers that were designed in the 80s, also 90s, except we're doing it inside the memory, if you will. Basically, we have communications via remote function calls, message queues, and we add graph processing specific prefetching mechanisms inside that I'm not going to talk about. Some of them take advantage of the message queue over here, the delay in processing the messages. Okay, I'm going to skip this. It's essentially put get-based remote function calls. And if you actually do this, what are the benefits that you would get? There are a lot of system design choices that go into this, of course. And we did this in simulation because we had no way of doing this inside the system. So if you look at the existing systems over here, this is a DDR3 based system. Its bandwidth exposed to the core is about 100 gigabytes per second. Hybrid memory cube, 3D stacked memory plus logic actually increased that to 600 gigabytes per second, but the interface is still the same. It's just a faster or higher bandwidth interface. And we also have another example over here. Because we cannot put complicated cores inside the logic layer because of thermal limits, we have in-order cores. So for comparison, we look at 512 in-order core-based system also. So if you look at Tesseract, it looks different because it doesn't have the processor-memory dichotomy, if you will. And it leads to 8 terabytes per second bandwidth exposed to the cores in aggregate to 512 cores over here. So the performance improvements that we get on 5 different graph processing algorithms on average are promising. It's about 9x without prefetching. If you actually do prefetching, because these in-order cores are not very powerful, they don't exploit all of the memory bandwidth that are exposed to them in the vaults. So if you do prefetching, you exploit that memory bandwidth and you increase the performance to about 14x. I believe we could have done better perhaps by optimizing the system, but 14x is not bad in this case. You cannot achieve this with at least the existing memory technologies over here. So some of the benefits are actually coming from bandwidth, some of the benefits are coming from changing the entire system design programming model, and it's kind of like half and half, but I'm not going to go into that detail here. But we basically can exploit about 2.9 terabytes per second of the 8 terabytes per second memory bandwidth that's available to the cores. And if you look at the energy reduction, it's about 8x overall, and we don't include the out-of-order cores over here. And there are more studies to be done over here. So essentially, energy consumption also improves. And there's more to talk about, but I don't have time to talk about that over here. It's a more detailed system design paper. So I think this gives an example of the potential benefits. If this 3D stacked memory exists, and if you have some layer, logic layer inside it, maybe you reconfigure it. Maybe it's a reconfigurable logic layer. You could do more inside it, and you could put these cores. You could potentially design a system that could do much better graph processing. And I believe graph processing is very fundamental still because a lot of the machine learning based systems are based on graph processing frameworks too. So similar along these lines, we recently looked at workloads from Google, but we didn't want to change the entire system in this case. we wanted to look at some key consumer workloads, understand their bottlenecks, and look at how we could actually change the system, not as much, but take advantage of 3D stacked memory by doing function offloading. So in this case, the programmer looks at the system, and this programmer is my student, Amirali. He actually looked at these, a bunch of workloads in consumer devices, and clearly energy consumption is a big bottleneck over here. And there are a bunch of workloads that are really interesting that we had our hands on at the time, and we examined them. And essentially, we quantified the energy cost of data movement, and we found out there's significant fraction of the total system energy spent on data movement. And we wanted to examine moving computation close to data to get rid of this data movement as much as possible. The challenge is, of course, again, limited area and energy budget that are especially stringent on these mobile devices. But also 3D stacked logic and memory has this area and energy budget also. So essentially, the observation is that a significant fraction of data movement often comes from simple functions, like copying and zeroing is an example. And you can design lightweight logic in 3D stacked memory to implement them inside the logic layer. You could do this using a small embedded low-power core that's similar to what we discussed with Tesseract earlier, or you could have small fixed function accelerators. And our results show that you could reduce energy and improve performance by about 55 to 54%. If these don't sound interesting, think about these as improving performance by 2x. People like 2x better. If you reduce something by 55%, 2x is how you improve. Anyway, so we did have a bunch of workload analysis. I'm not going to go into this in detail. I'm going to look at some of the things. I'll pick this one over here because it tends to be hot. But if you look at machine learning-based frameworks, you essentially do inference. And a significant fraction of the inference energy is actually spent on data movement. And some of that data movement comes from not moving the data to do the computation, not doing the computation, but actually preparing the data to do the computation. And that's packing and unpacking and quantization. And we actually quantify this in the paper. I'm not going to go into that in detail, but for example, whenever you move between stages, you actually change the matrix, pack them by reordering the elements of the matrices to minimize cache misses. And that leads to significant data movement. And you can see the numbers. They're not that important, but they're significant. And these are actually simple data reorganization processes that require simple arithmetic. And you could actually perform these relatively easily inside the logic layer. Quantization is another example. Essentially, you don't need full 32-bit floating point numbers to do the learning. You could reduce them. Actually, people are trying to get rid of as many bits as possible over here. People are trying to do binary neural networks, for example. In TensorFlow, you convert 32-bit floating points to 8-bit integers. And that takes a lot of data moment to be able to do that. And this is a very simple data conversion operation that you could easily do in memory without moving the data into the processor. If you actually had some simple primitives inside the logic layer, you could do these relatively easily. So these are some examples. There are a bunch of other examples. And actually, these are feasible to implement in processing in memory relatively easily. And we did some simulation. I'm not going to go into detail. You can read the paper. Essentially, we identified some of these functions. You can see that texture tiling, color bulleting, compression, decompression. There are a bunch of other stuff that we looked at in video playback and capture. And we put them in cores inside the logic layer or these special simple fixed function accelerators. Of course, the accelerators reduce the energy even more, but also these general purpose cores that are used for example, compression, reduce the energy significantly. So overall, the energy consumption reduces significantly for these particular functions. So of course, this is a tedious process. The programmer needs to do this. But I believe it's important to do this so that you could take advantage of a new architecture. And also performance improves. And again, an accelerator is much more efficient in improving performance compared to a general core, but the improvements are significant. So this is another example of taking advantage of 3D stacked memory, maybe not changing without changing the programming model significantly. Of course, there are some coherence issues that I'm not going to go into. These are related to adoption issues. Okay. We're also looking at GPU processing. So if you look at a GPU, GPUs are actually one of the most bandwidth bottleneck devices that we have today. You could offload some of the computation of the GPU into the logic layer, maybe some smaller GPUs over here. We've been examining that. You could get significant benefits out of this. And in this work, we wanted to actually look at doing this transparently to the programmer. The programmer doesn't change anything in the system. And you have a compiler that automatically does this. And once you start doing that, your benefits reduce. In this work, we showed that you could improve performance by about 30 to 50%. It's not, it's really 30 to 50%. It's not 2x, basically. In this case, it's 1.3x, 1.5x. So this is transparent, programmer transparent. I think whenever you go programmer transparent, it's not going to be easy. I believe this needs to be explored. But the bigger advantage is really coming from, in my opinion, modifying the applications to fit the architectures. Maybe after that, we can be programmer transparent. Okay, we've been looking at other things like exciting pointer chasing and 3D stacked memory. Because of the lower latencies in 3D stacked memory, you could actually improve performance a lot, and depending cache misses also. Okay. Any questions? How much time do we have?
Maybe 5 to 10 minutes.
5 to 10 minutes?
Oh,
okay.
So probably about 5 minutes.
Okay, let me briefly give you the idea on the minimal processing in memory support. I think this is very important. Whenever there's a new technology, it's really important to look at what can we maximally do with it and what can we minimally do with it. And whenever you want to look at what can we minimally do with it without changing the system, without changing the programming model, your performance benefits will go down. And that's what we did, again, in another paper that was concurrent with the first Tesseract paper that I mentioned. We wanted to have minimal cost, minimal changes to the system, no changes to the programming model. We want to keep the sequential programming model. And the idea in this case is to offload on an instruction basis operations to the engine in memory. We call this PIM-enabled instructions, processing in memory enabled instructions. So host processor does the translation so that you can keep the virtual memory. And you operate, this instruction operates only on a single cache block. So you don't need to deal with multiple cache block granularities. So coherence becomes much easier in this case, clearly. So for example, you program with these primitives, pim-add, and that gets translated to instructions like this. And also we had other dynamic decision mechanism that decides dynamically where to execute this instruction. Should you execute in the host processor? Should you execute in the main memory? Okay. I don't want to go into a lot more detail over here, but if you actually do this, then the key question is, what are the instructions? Do you want to have a pim-add? Maybe a good idea. How do you want to synchronize? When do you want to get notifications when this pim-add is done? Or do you actually synchronize at the end of a block? So we added these pim fences for that purpose. And we actually essentially designed the instructions to specialize to the applications at hand. So they're clear. If you have reconfigurable logic and if you have flexibility in your ISA, I think you can do a lot over here. But for example, we had an instruction that is a dot product that was good for the support vector machine. We had an instruction that did Euclidean distance for stream clustering. And you could see instructions like hash table probing that operate on cache block granularities. And the overall, again, I'm going to skip these, but basically, the overall speed ups we get are not 13x, as you could expect. It's about 47% with large input data sets. It's not bad, I think. But it doesn't exploit the full potential. But it also doesn't change the system significantly. This is a lot easier to program, in my opinion, and this is a lot fewer changes across the stack. So maybe this is a good way to start with in a general purpose manner. And I think industry is moving in this direction also. They're able to execute atomic operations in the memory controller, for example. But there is more to be done, in my opinion. Okay, so let's skip some of these over here. Essentially, we have this big challenge, I think, and I think we need to do this data-centric architecture design to overcome the energy and performance challenges. And I think, in the end, it boils down to data movement. We have this challenge because we're moving data too much in the system. That's causing the energy and performance bottlenecks. So there's a whole issue of how to enable adoption. I'll give you a couple of slides over here. Because it's a new technology, I think any new technology comes at a cost. Both real cost in terms of manufacturing, that's going to be true for processing in memory, and also adoption cost. And I think GPUs are an example of this. Data flow engines are an example of this. FPGAs are an example of this. FPGAs existed for a long time, but they've become popular recently, partly because of the scaling issues that we had in the systems, but also because some of these costs were amortized over time, right? And I believe processing in memory is no different from that. We need to essentially develop mechanisms to enable it. And I think there are a bunch of barriers to adoption, like applications, functionality, programming, interfaces, compiler and hardware support, system support, runtime systems, infrastructures. There's a lot over here. This is not meant to discourage, I think. I believe there's a lot of opportunity to research across the stack to enable something like this. And this is the research that we would like to do, I think, if you want to be forward-looking going into the future. And we recently written a paper that talks about some of these adoption challenges and some issues that we see in terms of future research directions in processing and memory. That's in a book chapter, but it's also an archive. Okay, let me conclude a little bit. We still have time, right? But I don't know if my computer has time. It decided to shut off over here. Okay. No, it's doing something that I don't recognize. If there's a question, I can take it while I'm trying to figure out what it's doing. Okay, maybe I'll do this very quickly. So I'm going to skip a bunch of these things. But I'm going to go back to this part. Any questions before I conclude, or if my computer lets me to conclude? I don't know what that is. That's interesting. Oh, the connection, maybe. Let me do this. Okay. Okay. It's not going to take more than 3.
Okay.
Is that okay?
Sure.
But it's going to be the most, I think, for me, the most fun part of the talk. If that's okay. Okay. So some famous architect said this: architecture should be based upon principle and not upon precedent. Anybody guess who this is? How about if I give you this picture? How about if I give you this picture? Probably you wouldn't guess, because this is a precedent-based design. It's not principle-based design. How about if I give you this picture? There you go. So he got it right, apparently, because you can recognize them based on the principle-based design, right? Frank Lloyd Wright. So if he were designing things based on precedent, he would be designing something like this. It's not bad. It works. We can tolerate it, perhaps. I don't mind it. Could be worse. But it's not like this. Clearly, this came at a much bigger cost, right? This is expensive. People needed to enable this, just like processing in memory, in my opinion. It was not as easy as the previous one. But it's a masterpiece, and it works nicely. Of course, you need to cut down the cost, and at some point, Frank Lloyd Wright didn't receive more money from the cost ones to actually continue his operation. Now that I'm in Zurich, I don't use this Pittsburgh landmark as much. I use, but there's a principle behind this, organic architecture, you can read about it. I use this one. This is a precedent-based design. It exists everywhere in Switzerland and a lot of Europe. You could call it boring. It works. It's not bad, but it's not like this. This is another architect who was hard-headed as the previous one. But if you look at this actually, do you know what this is? This is Bahnhof Stadelhofen in Zurich. And for the first time I went into it, I was really mesmerized because it has a principle. And it actually has, it's a zoomorphic design, essentially. It's like a bird. And the same architect repeated this principle. This is in Lisbon, if you're from Portugal. You know that it's the first place I went to Lisbon to see when I visited them. And you can see the, zoomorphic blueprints of the design. It's the same architect in Sevilla. What does this look like, you think? Harp? Yes. Bird, there you go. Actually, you have the same mindset as the architect, I think. Yeah, this is like a pigeon, according to the architect. Not everybody says it's a pigeon, but this is the same architect in Barcelona. Anyway, but this may be more familiar. This is the same architect. Has anybody guessed the architect? You know this probably. This is the Oculus in New York. It's caused a lot of pain to New Yorkers. It's $4 billion. It came at a cost. But now people go into it and they don't care about the cost. They forget about it. The new technology has been enabled basically. Once the new technology is enabled, you forget about the cost because you transition to this new technology at that point. And this architect is actually Santiago Calatrava. He turns out to be an ETH alumnus in civil engineering in PhD.